As you may have known, there are four fundamental forces that act on an airfoil, which includes lift, drag, weight, and thrust. However, for the purpose of this presentation, we will focus only on lift and drag. Lift and drag are composed of two other forces, which are normal force and axial force. The normal force acts perpendicular to the chord line, while the axial force acts along the chord line. With simple trigonometric applications, we can determine the equation of lift and drag based on the normal and axial forces. The normal and axial forces can be further split into components containing pressure and shear stress. Pressure is basically force per unit area. And shear stress is essentially a component of stress coplanar to the surface, which has the following formula. In which mu is the viscosity coefficient and dV over dy is the velocity gradient, which will be covered later when talking about boundary layers. These two are two of the 5 basic quantities in aerodynamics, which are density, temperature, and flow velocity, which is basically the velocity of moving particles at each point. Hence, from the components, we can derive the change in the normal force and the axial force on the upper surface, hence the subscript U. ds here is basically the change in distance across the surface. Now, if we were to draw the same components on the lower surface, we can derive the change in normal force on the lower surface. Combining the equations would give the formula of normal force. And the formula of axial force. Prime basically represents force per unit span, because we're considering only a 2D airfoil. Hence, it can be assumed that the span would be 1. This diagram is a summary of what we've covered. Using this diagram, we can also figure out the formula for moment on an airfoil. Assuming that we have a distance x from the leading edge, and a perpendicular distance y, we can essentially multiply the corresponding forces to these distances to calculate the moment. The formula of moment on the upper surface would be as follows. Similarly, we can derive the formula of moment on the lower surface. Combining the equations would give the formula of moment about the leading edge. The calculation of all these forces and moment proves tedious at times when only certain variables need to be changed. Hence, force and moment coefficients were created to facilitate this process. To derive these coefficients, we must use a technique called dimensional analysis, which is the study of the relationship between physical quantities with the help of dimensions. What we will employ is the Buckingham pi theorem, which allows solving for physical variables using dimensionless products. Essentially, it states that for n physical variables, we can write them as a set of n minus k pi products, with k being the number of fundamental dimensions that the relevant physical variables use. With these variables, we can write a function of n minus k pi products that equals to 0. Now each of these pi products would be dimensionless. So basically, the dimension of pi would be 1. Each of these pi products as proposed by the theorem can be rewritten as a number of k physical variables plus one more. Hence, which gives the following equations. Note that these repeating physical variables must include all of the fundamental dimensions. Now, to use the Buckingham pi theorem to derive the coefficients, we must first determine the relevant physical variables. Force in aerodynamics would be influenced by density, flow velocity, the size of the body, represented by the chord length, which is c, the fluid viscosity, which is represented by the viscosity coefficient mu, and the fluid compressibility, represented by the speed of sound a. These infinity subscripts denote the quantities of free stream, which is the undisturbed flow far ahead of the body. With this equation, we can simply move r to the other side to obtain a function that equates to 0. With regards to dimensional analysis, the dimension of r, denoted by r enclosed in square brackets, is as follows. This is basically due to Newton's second law. Density is basically mass over volume. Note that m is mass, L is length, and t is time. Similarly, we can write the dimensions of other variables. Since they only use at most 3 of these fundamental units, k equals 3. Because of that, f2 can be rewritten as a function of 3 pi products, since 6 minus 3 equals 3. Now, arbitrarily, density, velocity, and the chord length are selected as the repeating p physical variables. Hence, the pi products can be written as follows. So assuming pi1 equals the following expression, its dimensions can be derived. Since pi1 is dimensionless, the indices of the fundamental dimensions should add up to 0. We get the following simultaneous equations. Hence, we can solve for each variable. Hence, we get the following equation. Since multiplying pi1 by a pure number does not change its dimensions, it can be rewritten as follows. In a similar manner, we can solve for pi2 and pi3. The formula of pi2 and pi3 give us the Reynolds number and the Mach number respectively. Since all of our parameters are entailed in pi2 and pi3, it can be said that pi1 is a function of pi2 and pi3. Right. We can also replace c squared with s, the reference area. We have derived the coefficient of force plus two more important quantities, including Reynolds number, which is basically a measure of the ratio of inertia forces to viscous forces in a flow. So it's essentially a measure of how turbulent a flow is. Mach number is, as the equation says, the ratio of flow velocity to the speed of sound. This quantity is usually used to determine when shock waves form and the shape of the shock wave at different Mach speed. In order to effectively apply this into wind tunnel testing, we must be able to understand flow similarity. For two flows to be dynamically similar, the streamline's patterns must be similar. The distributions of velocity, pressure, and temperature must be similar, and as a consequence of this latter requirement, the force coefficients must also be the same. By applying the principles of dynamic similarity, we can simulate real-world situations with a smaller and less expensive model. And before one can effectively analyze the results of a wind tunnel test, they must first understand boundary layers. A boundary layer is essentially a thin viscous layer of a fluid in a flow immediately adjacent to the body. As you can see, this basically describes the velocity gradient seen in the formula for shear stress. since the air particles at the surface do not move due to the shear friction, and the air particles at the edge of the boundary layers move at a much faster speed, the velocity gradient is usually very large. So the boundary layer theory is usually dedicated to calculating this velocity gradient and the boundary layer thickness, denoted by lowercase delta. Two more concepts are required to be understood before moving to the CFD results. One is the Bernoulli's principle, which basically states that the points of higher fluid speed will have less pressure than points of slower fluid speed within a horizontal flow. So the equation would be as follows. Note that the second term on the right-hand side belongs to Archimedes' principle. Hence, it can be said that the Bernoulli's principle factors in speed to calculate for dynamic fluids rather than just static fluids. The second concept would be the circulation theory, which explains that the speed on the upper surface of an airfoil is faster than the speed on the lower surface, which creates a net circulation. This theory is one of the most complex theory in aerodynamics, hence we will not go deeper into it. We will only use its conclusions. Here are the results for the NACA 4415 simulation. The trend you may have noticed for velocity is that the area on top of the airfoil is brighter than the area below it, which means that the airflow on top is faster than the airflow below the airfoil, which confirms the circulation theory. As for pressure, the area on the upper surface is brighter than the area on the lower surface, which, according to this scale, means that the pressure on the upper surface is lower than the pressure on the bottom surface, which hence confirms the Bernoulli's principle. Here are the numerical results. As you can see, the coefficient of lift generally increases as the angle of attack increases. The same goes for the coefficient of drag. This makes sense because as the angle of attack increases, the curvature of the airfoil relative to the free stream is larger, which, according to the circulation theory, would increase the disparity in speeds on the upper and lower surfaces. This would thus increase lift and drag as pressure difference is increased, while the density, velocity, and reference area do not change. Here is the paper model of the NACA 4415 in a wind tunnel. If the Bernoulli's principle and the circulation theory are correct, we should see laminar flow between the edges of the airfoil and turbulent flow at the edge, due to the fluid's tendency to move from a high pressure area to a low pressure area. As you can see, as the thread is moved towards the edge, it spins more violently, suggesting that there is turbulence. We can amplify this effect by increasing the angle of attack. Laminar flow in between the edges and turbulent flow at the edge. Due to this phenomenon, the flow velocity is reduced, which increases drag. Hence, what one usually see at the tip of the wing are winglets, which prevents this turbulent flow at the edge. Assuming that this stand acts as a winglet, it can be seen that laminar instead of turbulent flow is produced on the other side. The only reason that the flow seems to be diverged is because of this obstacle. An understanding of the concepts and equations helps determine an airfoil's dynamic efficiency, stability, scale, shape, and more. In supersonic flights, to reduce shock waves at high Mach numbers, delta wings are used to split the flow into two perpendicular components, slowing down the flow over the wing. It can be inferred that lift and drag are also reduced based on the formula of the coefficients. One example would be the Concorde, a commercial supersonic aircraft. Its ogival wings create large turbulence on the top of the wing at low speeds, creating a large pressure difference sufficient to generate enough lift. However, at high speeds, the turbulence diminishes. As for space applications, blunt surfaces are used for re-entry aircraft to increase shockwave by heating the air around the body instead of the body itself. In the case of Mars Ingenuity, lift can be calculated in different environments using the coefficient of lift calculated on Earth. Aerodynamics are also heavily applied in automotive, especially F1 race cars. These are equipped with aerodynamic structures that maximize downforce while abating the effects of dirty air. These structures include a downward angled rear wing. It almost resembles an upside down airfoil. Another structure is the drag reduction system, which controls the rear wing's surface area. And according to the force coefficient, as we decrease the reference area, which in this case is the wing's surface area, we get a smaller force, which decreases drag.